We're going to continue our discussion of curve sketching and concavity, and we're going to look at another example, and this time we're going to look at a rational function. Let's consider the graph of f of x equals 2x minus 1 over x minus 4. Now, from your previous work in a pre-calculus class, you would have learned how to find vertical and horizontal asymptotes, so we're going to go ahead and discuss those or calculate those. You may have also discussed those in this course. So the vertical asymptote, remember, you find by what would make your denominator be equal to 0, but is not going to cause a hole in your graph so that you don't have a removable discontinuity. In this case, my vertical asymptote is going to occur at x equals 4. Now, to get my horizontal asymptote, you may recall that you do the limit as x approaches positive and negative infinity for your entire function. And as it turns out, if you do the limit on this function, you are going to get a value of 2, and so my horizontal asymptote would be y equals 2. Now those are really just going to aid me when I'm ready to sketch, but I want to go ahead and calculate those. So now let's go ahead and find our derivative. Now, because we have a rational function, we're going to find the derivative by doing the quotient rule. So my derivative would be x minus 4 times the derivative of the numerator, which would be 2, minus 2x minus 1 times the derivative of the denominator, which would be 1, over x minus 4 squared. But that's going to give me, I'm going to go ahead and do distributive property, 2x minus 8 minus 2x plus 1 over x minus 4 squared. But that's going to simplify down because we do have our 2x and our negative 2x that are going to cancel. So then I'm going to have just negative 7 over x minus 4 squared. Now remember that to get my critical points, because this is a rational function, I need to consider what makes this derivative either equal 0 or be undefined. Well, it equals 0 when the top is 0, but negative 7 is a constant, it's never 0. X minus 4 squared would be, if that's equal to 0, would make my fraction be undefined, so that would happen when x was 4. So that's my only critical point for my derivative. So let's pick some values on either side of that. So I'm going to go ahead and use 3 and 5. Now, if I'm very observant, I actually can tell that I don't need to substitute in numbers to this equation, but if you don't catch that, you'll actually be able to see it once you've figured out your signs. But look at what's happening here. X minus 4 quantity squared in the denominator is always going to be positive, no matter what you substitute in, because you're squaring it. And then on the top, in your numerator, you have negative 7. So you're always going to have a negative divided by a positive, which means your answers will always be negative. So even if I substitute in the 3 and the 5, I'll see that my derivative is going to be negative. So what that tells me is that on the domain of this function, which remember, x couldn't be equal to 4 from the original function because you would have division by 0, that this function is always decreasing. That also means that I can't have any relative maxes and mins. So I know that my function is always decreasing and no relative maxes or mins. Now let's continue on with using our second derivative. So we have that our first derivative was negative 7 over x minus 4 quantity squared, which actually I'm going to consider that as this problem just because it makes the derivative easier. So then f double prime would be equal to positive 14 x minus 4 to the negative 3 times 1, because the chain rule says take the derivative of the inside, but that's just going to be 14 over x minus 4 cubed. Now again, I want to find out what would make this 0 or undefined. Well, because the top is a constant, it's never 0, so the denominator is 0 at 4. So 4 is, again, the number I'm going to use on my second derivative sign chart. Now this time, because the bottom is being cubed, I do need to actually substitute in values because I'm not always going to be positive or negative. So let's use 3 and 5. So if I put 3 in, the top is always positive, so I don't have to worry about that. But then 3 minus 4 would be negative, and a negative cubed is negative. So I have a positive divided by a negative, so that's going to be negative. And from 5 on, if I put in 5, I'm going to have a positive on the top. 5 minus 4 would be a positive. Cubed is a positive. Positive divided by positive would be positive. So we do have concavity that I can label. So we know when we're concave up, our second derivative has to be positive. So this would be concave up from 4 to infinity. We're going to be concave down when our second derivative is negative, but that would be negative infinity to 4. And then it does appear that this has a point of inflection, but you have to be very careful about this. The point of inflection actually doesn't exist because 4, remember, was restricted from our domain. So even though we do have a change in concavity, the derivative, the second derivative, doesn't exist at 4, so that can't be a point of inflection. So we have no relative maxes or mins and no points of inflection. So let's put this together now and come up with our graph. So we know that our function is always decreasing. We have our concavity and we have our asymptotes. So let's start by plotting our asymptotes. We have a vertical asymptote at x equals 4 and a horizontal asymptote at y equals 2. Now, again, we know our function is always decreasing, and we know up to 4, so in this part, we have to be concave down. So we are decreasing and concave down. Well, the only way that that's going to fit in our graph would be if our picture looked like this, decreasing, concave down. Then the second part of the graph, because we have a vertical asymptote, we've got to skip what happens at x equals 4, is always decreasing again, but it has to be concave up. Well, that's only going to sketch in if I graph like that.